Picture an e-commerce search engine handling hundreds of millions of items for hundreds of millions of users, all within a few dozen milliseconds. Behind the scenes, the retrieval stage that decides which candidates even reach the ranker isn't one model but a committee of three. There's a lexical branch built on inverted indexes like BM25, a dense vector branch using something like DPR, and a collaborative filtering branch that leans on co-interaction history. Each branch has its weakness, the results get fused by hand-tuned merging rules, and everyone accepts the redundancy as the price of robustness. The big question this paper asks is whether a single generative model can finally collapse this whole stage into one clean policy. You'd think generative retrieval would already have solved this. The idea is elegant. Train a sequence model to auto-regressively generate an item identifier given the query and user context, the same way a language model generates tokens. And indeed, methods like Tiger, DSI, and the author's own prior work OneSearch have shown that this works at production scale. But here's the catch the paper centers on, and it's a really interesting one. The inverted index branch actually converts below the platform average. By pure retrieval quality, it deserves to be retired. Yet it stubbornly persists, and the reason has nothing to do with recall. It persists because it's editable. When a viral product like Labubu starts trending at noon, the operations team can bind that new term to a target set of items by updating a dictionary, refresh the index, and have it live by dinner. No model retraining required. The authors call this the editability paradox. Every existing generative method loses this property. Closed-codebook approaches bind each identifier slot to a quantized embedding fixed at training time. Open vocabulary approaches generate free-form text and hope the model generalizes to new terms, with no explicit way to route a new word to specific items. 1. Retrieval's core insight is to build editability directly into the identifier scheme itself. The method is called Keyword-Aligned Encoding, or KAE. Instead of each identifier position being a quantized embedding centroid, each position corresponds to an interpretable key attribute word drawn from a production attribute dictionary. Think of it like this. Rather than encoding an item as an opaque 6-digit hash, you encode it as a 6-slot tuple, where the first slot is the product entity, the second slot is the brand, the third is material, and so on. The trick that makes editability work is reserving a small block of slots in each position's codebook that are left intentionally unbound during training. When Labubu starts trending, operations adds it to the dictionary, points it at a reserved slot, links that slot to a target item set, and the policy can already emit that slot at decode time because it was trained as a generic identity routing target. Let me walk through the architecture more carefully. The team starts with 18 fine-grained attribute categories that an internal extraction pipeline tags, things like entity, brand, color, material, scene, function, and so on. 18 positions in an identifier would be too expensive auto-regressively, so they merge categories using an information-theoretic agglomerative clustering. The distance between two categories is the symmetric conditional entropy, essentially asking how much information you'd lose if you forced one category to stand in for the other. They run the merge at every possible group count, plot cumulative information loss, find the knee of the curve at 6 groups, and that's their identifier length. The entity category is held out as a singleton because it's the noun that everything else attaches to. Within each of the 6 codebook positions, capacity is allocated non-uniformly. The 3 positions corresponding to denser attribute groups get 2048 slots. The lighter 3 get 1024. Each codebook has a 4-block layout. Index 0 means the attribute is absent. Then a block of cluster centroids from k-means over tailword embeddings. Then a block of solo slots for head words that get their own dedicated identifier. Then 10 reserved slots at the end that carry no binding during training. That gives a total alphabet of about 9,276 tokens added to the language model vocabulary. The training itself uses BART-base as the encoder-decoder backbone, and the authors run 4 stages of supervised fine-tuning that map cleanly onto different responsibilities. Stage 0 is attribute to SAD alignment. teaching the model the bidirectional mapping between each populated slot and its attribute word. This anchors the alphabet semantically before any retrieval objective gets introduced. Stage 1 is content alignment, pairing queries and item titles with their full identifiers. This is where most retrieval quality gets installed. Stage 2 introduces collaborative co-occurrence, pairing query identifiers with the identifiers of items that users actually bought after that query. This is the load-bearing stage for editability, because it teaches the policy that a query identifier prefix should route to compatible item identifier prefixes. Stage 3 is personalized retrieval with user context, and crucially, it includes a tiny auxiliary block on the order of 1 part in 100,000 that exercises every reserved slot as a word-agnostic identity router. This last piece matters because tokens that never appear as targets accumulate only negative gradient and get suppressed at decoding. So this supervision keeps the reserved slots immutable without binding them to any specific meaning. When a new trending word arrives, here's the magic moment. Operations adds the word to the dictionary linked to a reserved slot. At query time, the Aho-Korasic string matcher deterministically encodes any query containing the word into that slot. The policy, having learned generic identity routing, decodes an item identifier prefix matching that slot. The slot-to-item lookup table, which operations also updated, returns the bound item set. No retraining, no policy update takes effect within hours. The experimental results are pretty striking. On a benchmark of 5 million real traffic requests, OneRetrieval matches the deep recall performance of OneSearch, which is the author's own strongest generative baseline, with hit rate at 350 of about 0.55 on orders and 0.61 on clicks. OneSearch actually wins on the shallow cutoffs and mean reciprocal rank because it's tuned for end-to-end ranking precision, but the two converge at depth, which is what matters for a recall branch. The real story is on editability. The authors design an intervention probe where they fabricate 2,000 new words outside the dictionary, inject them, and measure how well each method routes them. KAE achieves an intervention hit rate of about 0.08 against roughly 0.03 for the various quantization codebooks like RQVAE, RQK-means, and RQOPQ. That's more than an order of magnitude difference, and the authors argue convincingly that this gap is structural, not a tuning artifact. A quantization codebook fundamentally cannot give operations a controllable route from a specific new word to a specific reserved code. The activation rate against the actual BM25 inverted index incumbent reaches 55% compared to BM25's 76%, while more than doubling retrieval quality. So OneRetrieval recovers about 3/4 of the editability of the lexical branch inside a model that's far stronger at recall. Online, the results validate the offline picture. Replacing just the inverted index branch lifted order volume by 0.71% with statistical significance. Then they ran a more aggressive test replacing both the inverted index and the dense vector branches with OneRetrieval alone. Conversion stayed flat, but click-through rate rose 0.82% with significance. That's the headline result. One generative model can subsume nearly the entire multi-branch recall stage without losing conversion. Now for the honest limitations. OneRetrieval lags OneSearch on top of list precision because it's optimized for deep recall, not the precise top placement that mean reciprocal rank rewards. The reserved slot routing is a trained behavior rather than a hard guarantee, so the editability is statistical, not deterministic. The activation rate of 55% is real, but it's not the 76% of the inverted index. The reserved slot budget is only 60 tokens total, which the authors say absorbs a weekly trend cycle but would need expansion for longer tail catalogs. And the whole approach depends on having a rich attribute extraction pipeline producing globally consistent tags, which is a significant infrastructure investment that not every platform has. Now, let's walk through some questions you might have after hearing all of this. First question: why does reserving a few slots in each codebook actually let the model emit them at decode time when those slots were never bound to a specific meaning during training? This is the cleverest piece of the design. During training, the reserved slots are exposed to the policy only as identity routing targets, meaning the model sees examples where the input prefix contains the reserved slot and the target output also contains it. So the model learns the generic behavior that if you see a reserved slot in the query identifier, copy it forward to the item identifier. The slot has no semantic meaning yet, but the model knows how to handle it syntactically. When operations later binds a real word to that slot, the encoder deterministically places that word into the slot via dictionary lookup, and the policy just executes the copy behavior it already learned. Second question, why not just use a hierarchical encoding where, say, the brand position depends on which entity was predicted first? Intuitively, that seems better because the same brand could mean different things in different product categories. The authors actually tested this and it underperformed. 3 reasons. Hierarchical encoding turns the slot-to-meaning relation from a function into a one-to-many mapping, which dilutes the language model prior the attribute alignment stage is built to exploit. It fragments the training signal for any attribute word that appears across multiple entities. And in an autoregressive decoder, an error at the entity position cascades forward, which is especially painful under unconstrained beam search where there's no prefix tree to correct mistakes. Third question. If the inverted index converts below average, why does replacing it actually lift conversion rather than just replacing one mediocre branch with another? The key is that the inverted index converts poorly because it's lexically literal. It matches the surface string of the query rather than the underlying intent. OneRetrieval's keyword-aligned encoding decomposes a query into its semantic attribute words and matches items by those attributes. So it surfaces items that fit what the user actually wants rather than items that happen to contain the query string. The manual side-by-side evaluation confirmed this with significant wins on query item relevance and item quality, not just on the business metrics. For large-scale recommendation systems serving billions of users, the most directly transferable idea here is the extensible codebook pattern. Production recommendation stacks routinely struggle with cold start for new content, new creators, new product launches, or trending topics that emerge between training cycles. Most generative recommender designs being explored in industry today, things like semantic IDs for video or product retrieval, share the same closed-codebook weakness that OneRetrieval critiques. Reserving a slot budget in each codebook position, training the policy with word-agnostic identity routing supervision so those slots remain immutable, and pushing the actual binding into an upstream dictionary refreshable on the order of hours, gives you a deterministic intervention path that no embedding quantization scheme can match. This matters concretely for editorial overrides during live events, for promoting a new creator into a community where they have no interaction history, and for responding to viral content where the daily training cadence simply isn't fast enough. Beyond the editability mechanism, the 4-stage training decomposition is worth borrowing too. The clean separation between alphabet anchoring, content alignment, collaborative co-occurrence, and personalized retrieval lets each stage take responsibility for one capability, which is a much more debuggable structure than the typical end-to-end retrieval training. And the broader bet that a single generative model with the right identifier scheme can subsume multiple retrieval branches without losing conversion is a serious shot at simplifying the engineering and operational burden of the multi-branch retrieval architectures that dominate production recommender systems today.